This is the next video in the chapter on stoichiometry of chemical equations. We just learned about what solubility was as we talk about precipitation reactions, and now we're going to use the solubility rules to predict whether a particular mixture is going to form a precipitate. So these solubility rules are rules that I'm going to give you to use on your worksheets and tests, but I wrote them here to be useful. So please pause the video here and take a second to write these down so that this video doesn't have to last for a million years. Okay, so these 6 solubility rules are general guidelines for you for when you have a solute dissolved in aqueous solution to predict whether a particular ionic compound is going to be dissolved aqueous or a solid in the solution. So we'll read through these together so we can identify the important parts. So the way these rules work is sometimes we're going to be able to follow all the rules we need to, and some of times we're not going to be able to follow all the rules. So if there are 2 rules we need to use that conflict, we are going to break the rules from the bottom. So if both of the rules can't be true, we ignore the rule that's lower and we follow the rule that's higher. So the first rule says salts of group 1 cations and this polyatomic cation, ammonium, are soluble. So we'll put a green box around that one because it's soluble. Some of these rules are about solubility and some of the rules are about insolubility. So you'll have to be careful and read carefully. Rule 2, nitrates, acetates, and perchlorates are soluble. This is where our knowledge of polyatomic ions becomes particularly useful, but I don't think we covered this one, perchlorate. So perchlorate is a chlorine-oxygen compound, polyatomic anion, specifically 1 chlorine and 4 oxygens with a 1- charge. So now you can recognize a perchlorate. Rule number 3, salts of silver, lead, and mercury 1 are insoluble. So these salts are usually exceptions to the solubilities. Rule 4, chlorides, bromides, and iodides are soluble. So we'd expect to see those forming aqueous ions in solution. Rule 5, carbonates, phosphates, sulfides, oxides, and hydroxides are insoluble. There's a few more exceptions here. And rule 6, sulfates are soluble. Okay, so you'll start to see these general trends, and you'll probably even be able to recognize some of these rules by a while without looking because you'll get used to seeing these compounds. But we can use these rules to help us make predictions. So to start simply, we can just look at an ionic compound and use the rules to predict whether that compound will be soluble in water. Because these solubility rules are specifically only for aqueous solutions. So let's do a couple of examples. I've got 3 molecules written here, and let's identify which rule in the list refers to each of the different ions, and then we'll predict whether the compounds are soluble or not. So the first compound is sodium chloride. We can see sodium is a group 1 cation. Let's show the table here. So group 1 is not hydrogen. Hydrogen doesn't really belong here. Lithium, sodium, potassium, rubidium, cesium, francium. But most of the time we just see these first 3. So lithium, sodium, and potassium, those cations are going to be soluble. So rule number 1 says that we predict sodium is soluble. For chloride, we see that in rule number 4. Chlorides, bromides, and iodides are soluble. So rule number 1 says soluble, rule number 4 says soluble, and they're in agreement. So this sodium chloride is going to be soluble. And that seems to line up with what we know from experience. We know we can dissolve lots and lots of salt in our water. Okay, let's look at the next one, silver. Silver is in rule number 3. Salts of silver, lead, and mercury 1 are insoluble. So rule number 3 says this compound will be insoluble. And then iodide is in rule 4. Chlorides, bromides, and iodides are soluble. So this is the first case where we've seen two rules conflicting. One rule says the compound should be insoluble. One rule says the compound should be soluble. So in this case, remember we said we break from the bottom. So rule number 4 is farther down the list. So we're going to ignore that one. And we're going to listen to the lower numbered list. We're going to predict this compound is going to be insoluble in water because of that silver. And for our final one, the silver nitrate, we have got silver again. That's rule number 3, predicts insoluble. And then nitrate, here's here in rule number 2. Nitrates, acetates, and perchlorates are soluble. So in this case, we have two conflicting rules again, but this time the insoluble prediction is lower down in the list. The soluble is higher in the list. So we're going to go with silver nitrate, soluble. And you'll see that that's usually true. Nitrates are almost always soluble. So now that we can predict the solubility of individual molecular ionic compounds, we can take even one step further back and predict whether a solid compound is going to occur at all. I need to stop talking while I'm writing. We can use these rules also to predict whether a precipitation reaction will occur in a particular solution. So if I take two salts and I mix them together, am I going to get a solid, or am I just going to get a mixture of ions? So we have a strategy. We have the rules, of course, to help us, but there's a few other things involved in the process. So let's get our strategy straight before we move on to the examples. So the first thing we're going to do is we're going to identify what those ions are. We're going to identify the cations we have to work with and the anions we have to work with. Then once we know what all the ions are, we're going to determine the possible products. We know we have to combine cations with anions, so there's only so many combinations that we can make. Then we're going to look at each of those products that we can make, and we are going to predict the solubility of the products. So that's what we just did here in our last example. When given a compound, predict its solubility. So that's the middle. And then we're either going to have an insoluble solid or we're going to have all soluble. And so we'll have one rule for each of those cases. So if yes, if there is something insoluble that's formed, then that means a reaction is occurring in that case. And so if a reaction is occurring, we're going to balance the net ionic equation to emphasize which ions are actually involved in producing that solid. The other case is if all products are soluble. If every combination of cation and anion yields a soluble product, then you don't have a reaction. So no reaction occurs. And if that happens, we are just going to write the words no reaction after our reaction arrow. Oof, we are almost done, which is good because my hand is getting tired. So keep that strategy handy and those solubility rules handy. We are going to look at the following two examples, and we are going to try to predict what the products are and whether any of them are going to be solid precipitates. Okay, so the first reaction we're going to look at is this one, lead nitrate and potassium iodide. So our process says that the first thing we should do is identify the cations and the anions. So we can do that. Lead is going to be our cation. Nitrate is going to be our anion. Potassium is going to be our cation. Iodide is going to be our anion. Let's go a step further and write them out as ions so we can make sure we get the charges right. So we've got lead, and lead, I think, usually has a charge of 2+, but we can make sure by writing the other one. The other one is nitrate, and we know the charge of that one. Nitrate is always a -1. And if there's a -1 and there are 2 of those ions in this formula unit, then we need to have a +2 on the lead to make sure. So lead 2+, aqueous, and nitrate, and there are 2 of those, 2 nitrates, and there's going to be a potassium plus, and there's going to be an iodide minus. So that's where we're starting. So now we need to predict what our possible products will be that can be formed. And this is going to be pretty straightforward since you know all about ionic and covalent compounds. We know that every ionic compound needs to be a combination of a cation and an anion. We can't put 2 cations together, and we can't put 2 anions together. So we know that the lead is going to be in one compound, and we know that the potassium is going to be in another compound, but they're both cations, so they cannot be together. And each of them is going to get paired with an anion. So let's see, lead was with nitrate before, so now we'll put the nitrate with the potassium, and potassium was iodide before, so now we'll put the potassium with the lead. And then we need to make sure these products that we formed have the correct number of ions. So we know iodide has a charge of -1, and the lead has a charge of +2. So we need to swap the charges into the opposite subscripts, so that iodide needs a 2 subscript. Over here, nitrate has a charge of -1, potassium has a charge of +1, so those are just 1s and those are solid. Okay, so let's check the list again. Identify cations and anions and determine possible products. The next one is to predict the solubility of the products. So where are our solubility rules? Here we go. Okay, so lead, do we have a rule about lead? Yes, rule number 3 says it's going to be insoluble. And iodide is in rule number 4, which predicts it's going to be soluble. Potassium is in rule number 1, which predicts it'll be soluble. And nitrate is in rule number 2, which predicts it will be soluble. All right. So reviewing that information, insoluble versus soluble. Soluble is from rule 4 and insoluble is from rule 3. So this one is going to be insoluble. So we can write a solid next to that one. And both of these predict soluble. So we can write an aqueous next to that one. Okay, and in our strategy here, predict the solubility. If there is an insoluble product, which there is, we are going to balance with the net ionic equation. So I always find it easier to start with molecular and work my way to net ionic. It is totally up to you if you'd like to skip all the way straight to net ionic equation. Okay, so molecular equation. Aqueous lead nitrate plus aqueous potassium iodide goes to solid lead iodide plus aqueous potassium nitrate. So we've taken the 2 compounds we were given, gone slightly off the screen, and we have the 2 compounds we made. Remember to include the phases, either solid or aqueous, so you can remember where your solid is that you said you formed. And then we need to stop here for a second and balance. Let's see, there's one lead and one lead. We can balance this entire nitrate group as a unit instead of doing it as nitrogens and oxygens. There are 2 nitrates and 1 nitrate here. So we'll put a 2 in front of potassium nitrate. So now there's 2 nitrates on each side. We made 2 potassiums on the product side. So now we need 2 potassiums on the reactant side, 2 and 2. And then we've got 2 iodides and 2 iodides. So we've got a couple of coefficients. So now we are balanced. We can go ahead and move on to the ionic equation. So ionic equation makes all of the aqueous compounds into ions. So we're going to have lead 2 plus aqueous. We're going to have 2 nitrates. There were 2 of them here. We are going to have 2 potassium cations because of that coefficient, and 2 iodide anions because of the coefficient. I'm going to start a new line because this is super long. Remember that for solids, we leave the solid as it is, as one big piece, because that is not going to dissociate in solution. Then we're going to have 2 potassium cations and 2 nitrates anions. Okay, and so our final step that the equation or the problem actually asked for was the net ionic equation. And net ionic equation means we leave out spectators. So we see lead is not present on both sides as an ion, but nitrate is, and potassium is. Iodide is an ion on this side and a solid on that side, so we'll leave it. So we're going to leave out the spectator ions. We'll leave a note here for our future selves, so we remember what the heck we were doing. Okay, so the lead is still here. Lead 2 plus aqueous. The iodide is still here. 2 iodide, aqueous, and we form that lead iodide salt, which is a solid. And that is our completed net ionic equation. So predict the products of the following reaction. We predict that our product is going to be solid lead iodide salt. All right, there is another equation. It's kind of hard to see now that I've written a whole bunch of stuff, but this is our second example. Second example is ammonium sulfate plus zinc chloride. So same deal. We identify our cations and our anions. So ammonium is a cation, zinc is a cation, sulfate is an anion, and chloride is an anion. Let's see if we can figure out the charges without writing them this time. I remember sulfate. I remember sulfate is always -2. And I remember that ammonium is always +1. And there are 2 of those. So +2 -2 is 0. Zinc, I'm not sure about, but chloride I know is -1. And there are 2 of those. So zinc is going to be a +2. So our possible ions are ammonium plus, sulfate 2-, zinc 2+, and chloride 1-. So we can predict our possible products. I like to just write the 2 cations in the same order and then just swap the anions. Okay, so ammonium was paired with sulfate last time. So let's pair ammonium with the other anion, chloride. And this has a +1 charge and this has a -1 charge. So we just need one of each. And zinc was paired with chloride last time. So let's try pairing it with sulfate this time. Sulfate has a -2 charge and zinc has a +2 charge. So we just need one of each of those. Okay, so now we need to check our solubility rules. I've already forgotten what we're doing. Ammonium, let's see. Ammonium is in rule number 1 as soluble. Chloride is in rule number 4 as soluble. Zinc, we don't have a rule about zinc, so it looks like we're just going to have to go based on the other one. And sulfates is in rule number 6. Sulfates are soluble. So not every ion is included. That is not an all-encompassing solubility list. So sometimes we just have to go based on what is there. So all of these rules say that the ammonium chloride is going to be soluble. And based on the information that we have, that suggests that zinc sulfate is going to be soluble as well. So we can add a little aqueous subscript to both of them. And according to our rules, if there are no insoluble products or nothing is insoluble, we just write our reaction as no reaction. So we'll go ahead and write it again to make it really obvious what our answer is. Aqueous ammonium sulfate plus aqueous zinc chloride goes to no reaction. And this is very normal. We don't want a reaction to happen every time that we mix anything in water. That would be a real drag. We'll put a box around this one too. So sometimes you dissolve an ionic compound in water because you just want it to be dissolved. And sometimes you would dissolve ionic compounds in water when you want a solid to produce. So we just need to be able to figure out, based on our solubility rules, based on what we know about metals and nonmetals and their usual charges, based on polyatomic ions that we know very well, and based on cations and anions, what are the possible products? Are they going to be soluble, and will there be a solid at the bottom of the flask? We will move on to acid and base reactions next time.